There we go. Hello, 8th grade. Welcome to class, I guess, for at least the next couple weeks. We'll be posting videos for each lesson online so you guys can watch. It's basically just going to be going through the PowerPoint and me explaining just like we would in class. Let's get started. Alright, so we're in Chapter 10, which is the chemistry of living systems. So Chapter 8, 9, and 10 are the end of our chemistry sections. So this is the last part of the chemistry. And we're actually kind of merging chemistry with biology for this section. You'll notice this says living systems. And that means animals, right? Animals, humans, bacteria, and even larger than that, it's also the combination of how you eat plants, but then when you die, plants eat you kind of thing, So it's this whole, all living systems, not just singular, but also groups of them. So think of the things you have been doing today: eating, breathing, moving, and reading. All of these activities involve atoms and chemical reactions. Even when you're sitting still, atoms in your body are rearranging into different combinations of molecules. So I assume you just ate, at least recently, because that's what kids do. They just eat all the time. The stuff that you're eating is being broken down and rearranged. So remember, the matter can't be destroyed, but it can be broken up into different things. When it comes down to it, the basic elements that everything needs to live, most things are pretty much the same. We all need carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, which is this list of stuff right here. We all pretty much need that stuff to live. And if you added up all of the living matter on Earth, we get this word called biomass. It's the total mass of all living matter on Earth. This includes plants and animals and bacteria and stuff like that. Anything that was alive, if we add up the mass, it's the biomass. Living organisms like you and me, or the plants, get these elements from their environments, which makes sense, right? You eat an animal who ate a plant who got the nutrients from the ground. That's how nutrients work. These elements flow through the environment in natural cycles. Here we see the human body is composed of primarily 4 elements: oxygen, carbon, hydrogen, nitrogen, and there's 3.7% other stuff. That other stuff includes some metals that you'd be surprised that we even have, like copper and magnesium and iron. All that stuff is in our body right now, and we can't actually function without it, but for the most part it's these 4 guys. Keep in mind that, remember, water is hydrogen and oxygen, so that's why those numbers are so big. At this point, I suggest scrolling down to the comments and watching video number 1. I don't want to watch it on this PowerPoint because then it makes this video longer than it needs to be, and my computer kind of struggles with that. Okay, so this is assuming you just watched that video a second ago. So all the elements essential to life flow through food webs that are part of natural cycles. So you might have heard of a food chain. Let's say a little berry gets eaten by a mouse, and then a cat eats the mouse. That's a food chain. Food webs are a little more in-depth. For example, the berry might get eaten by a rat, but it's also eaten by a deer, right? And the cat might eat the mouse, but the cat's not going to eat the deer. But something bigger than that, let's just say a wolf nearby will eat both a deer and a mouse and a cat, right? So it's a food web. There's all sorts of different things that connect with each other. Different animals eat different plants, and they also eat other animals. So it gets complicated, and that's why we use the term web instead of just a chain. So the first thing, the carbon cycle, just describes how carbon moves from the atmosphere into plants. Okay, so how carbon moves from the atmosphere going into the plants, from the plants going into the animals, and then eventually as waste into the environment. That's exactly what you think it is, the waste after you're done eating. Another way carbon can be released is into the atmosphere when fossil fuels burn. and that they're called fossil fuels because it's like it used to be living organisms, so they call it fossil fuels because it's kind of catchy. But essentially, that carbon was locked up underground. By burning it, we release that carbon into the atmosphere. There's other things go through cycles as well, such as nitrogen and phosphorus. At this point, you should probably pause this video and scroll down and watch part 2. Okay, so this is assuming you watched both of those videos already. So here we see carbon and oxygen are cycled throughout the environment by natural processes as well as man-made processes. So the plant, let's just start with the plant, I guess. Plant takes in carbon dioxide from the atmosphere. You guys have probably heard, like, if when you breathe in, you take the oxygen that the plants make, and you breathe out the carbon dioxide. And the plant uses the carbon dioxide to make more oxygen in this cycle. And that is true. That is a cycle. Right? That is a cycle. But the plant also uses some of that carbon. Like the carbon doesn't get spat back out. The carbon is used to make sugar molecules. So in this case, to make a fruit, whatever this is. I can't tell because the picture's so bad. Maybe it's an orange or an apple or something. I don't know. So the plant takes literally the carbon atoms you guys are breathing out right now. A plant can take that and turn it into a sugar that becomes part of a fruit. So the stuff you're breathing out right now can end up being literally a fruit. The fruit falls down on the ground, and then animals can break down the sugar molecules found in food as energy. Well, what happens when you break down sugar molecules? If you eat something and you break it down, your body gets rid of it. One way is that way. Another way is you breathe out some of it. You breathe it out in the form of carbon dioxide. So you see this whole pattern? You breathe out carbon dioxide. The plant turns that carbon part of carbon dioxide into a sugar. You eat the sugar, and your body uses the energy, and you breathe out carbon dioxide. So that's one cycle. We can interrupt this cycle by burning fossil fuels. So most of the time it goes like this, but every once in a while, like for example, when you drive in your car's releasing exhaust. That carbon that's being released has been stuck underground for who knows how long, until some oil rig somewhere pulled it up out of the ground, and we refined it into gas, and then your car burned it, and now it's in the atmosphere. Now trees can still use that carbon dioxide. Trees can still use that. It's the same stuff that you're breathing out. It's the same, some of the stuff, same stuff up here. So trees can still use that to make sugars, to make fruit for things to eat. So the carbon is just getting thrown around in this cycle, and that's why it's called the carbon cycle. When you die, bacteria and plants will essentially use any materials you're not using because you're dead and make a tree and a bush and stuff like that, and then the whole cycle starts all over again. So how is carbon used in the bodies of animals, and where is it obtained? So remember, carbon in animals, we use it for like cellular processes. So breaking down your food, we need some carbon for that. Building pieces of yourself, we need carbon for that. Where is it obtained? Well, we eat plants. And if you don't eat plants, then you eat animals who ate plants, right? So either way, the carbon eventually gets to you, whether directly from the plant or from an animal who ate the plant. Either way, we're getting carbon from plants. So just like the carbon cycle, we have something called the nitrogen cycle. In this case, nitrogen-fixing bacteria convert nitrogen from the Earth's atmosphere into nitrogen compounds plants can use. The nitrogen that plants use is passed on through the food web to plant consumers and on to other consumers. So right now, if you take a deep breath and let it out, about 75% of the stuff you just breathed in was nitrogen. Our bodies can't use it. Our bodies don't even care. Air is just mostly nitrogen sitting there not doing anything. But these bacteria in the soil can actually grab that and turn it into useful things that a plant can use. And then if we eat the plant, then we get those useful things. You see how that works? We cannot get it out of the air, but the bacteria can get it out of the air and give it to the plants. If we then eat the plants, we get the good nitrogen. Phosphorus also follows a cycle. So if there's a rock somewhere, and let's say a bunch of wind and water hits it, you can break down that rock and phosphorus can fall out of it. Well, plants use phosphorus to build themselves. So if you get the theme here, if you ever eat a plant, you're eating phosphorus, therefore you get the phosphorus that you need. And again, even if you don't eat plants, you hate vegetables, you're still eating animals who ate plants before. So you still have that, you're still getting the materials that you need that way. Does that make sense? I'm assuming you said yes. If not, then watch the video or go on the Google Hangouts on Tuesdays and Thursdays. So both of these are still a cycle. In both of these cases, nitrogen and phosphorus, when you die, bacteria and plants will use this stuff to make new stuff for something else to eat. Okay? Which means all of the pieces of stuff that you are right now at one point was something else. Which is kind of crazy, right? You have a piece of phosphorus in you that might have been in a rock for all of its life. Well, life doesn't make sense for a rock, but you know what I mean? For all of history, the phosphorus could have been stuck in a rock. Some of the nitrogen you're made of maybe was part of George Washington. I don't know. Statistically, that's not going to happen, but I mean, it's possible. Here we see an example of nitrogen. Nitrogen in the air gets used by the bacteria. The bacteria make it into useful compounds that the plants can soak up. This duck eats the plants, and you eat the duck, and therefore you get the good nitrogen compounds down here. There's actually a crazy way that this can bypass all this stuff, and that's lightning. Lightning can actually do what bacteria can do as well. Like if a lightning strikes, it makes these nitrogen compounds that we need. So thanks to lightning and bacteria, we can actually ingest this nitrogen. So of course, whenever you guys think of natural cycles, you probably go to the water cycle. You've probably been learning that since you were old enough to remember. So in addition to just these pure elements like carbon and nitrogen and stuff like that, we also need water. The fluid properties of water allow blood to flow and carry substances throughout the body. The liquid portion of blood, which is called plasma, is 90% water. 90% water. 10% is just a bunch of other jumble of stuff. Actually really valuable. Really valuable. You can donate that and make a decent amount of money. So water is unique because it requires a lot of heat in order to change temperature, which means it takes a lot of heat for you to change temperatures because you are mostly water. And that's a good thing. Because if you ever think about a hot day and you put your hand on a piece of metal and it burns, that's because metal does not require much heat to change temperature. But water requires a lot. So what that means is you get to stay the same temperature a little easier than things like metal can or like asphalt can. When it's really cold, you know metal poles get extremely cold. If you were as cold as the actual metal pole was, you'd be dead. But thanks to water requiring a bunch of heat, it keeps you from changing your temperature too much. And another unique property about water, solid water, which is otherwise known as ice, is less dense than liquid water, so it actually floats. That's kind of obvious, you know ice floats, but that's not true for everything. A lot of the times the solid version of whatever we're talking about should be more dense than the liquid version. But with water, that is not the case. Here we see icebergs and little penguins chilling. And here we see blood separated into plasma and red blood cells. So both are useful. I do know you can donate both. Sometimes plasma is a little more useful to donate, but I know they can essentially take your blood out, do this, give you your blood cells back, and then just kind of mix it with some like sugar water to summarize, and pump that back in your body, and you kind of don't really feel much different if you're healthy. But you can donate your plasma to help other people who might not have plasma, because that's really useful for certain people with certain medical conditions. So continuing on with why water is important, We know it's a polar molecule. We learned about that in a previous chapter. That means it's really good at dissolving things. It's really good at dissolving things. Remember, polar means a molecule has a positive and negative end because of unequal sharings of electrons. So it's like tiny little magnets. And remember, nonpolar molecules share electrons equally, which means they don't have oppositely charged ends. Okay? So a polar molecule would be like water. A nonpolar molecule is like oil. That is why oil and water do not mix, because they are not the same type of molecule. So between each water molecule, whether in ice or in water, there's tiny little almost chemical bonds called hydrogen bonds. And this is the reason why water can do so many kind of unique things, why it's kind of special. So we learned about covalent bonds, right? Where one atom is sharing electrons with another thing. Well, because these are polar, this oxygen atom's just a little bit more negative than it should be, and this hydrogen's just a little bit more positive than it should be. So what happens is there's like a kind of chemical bond right here. They're not really sharing electrons, they're just kind of hanging out together because this is negative and this is positive, and they're kind of attracted to each other. So what happens is that's how you get these cool formations, and that's why snowflakes always look like cool crystals. Because you get these hydrogen bonds where there's no real electron sharing. I mean, for the purposes of this class, we don't have to worry about that. But there's still a type of bond there, and that's what gives water so many unique properties. The covalent bond, of course, is important, but this hydrogen bond between water molecules is what gives so many special characteristics to water. So here we see a property of water and why it would be beneficial to living things. Hydrogen bonds hold water molecules together, right? What that means is that leaves are able to pull water up from the roots. And small insects can walk on water because the water is holding itself together. Hydrogen bonds absorb heat when they break and release heat when they form, minimizing temperature changes. That helps us stabilize our internal temperature. That way we don't freeze when it's freezing outside. You ever think about that? It's freezing outside, yet we don't freeze. Now, of course, we have clothes to help with that, but also it takes a long time for us to freeze even if we didn't, because water's so good at stabilizing the temperature. In order for water to evaporate, you got to break a bunch of hydrogen bonds. The evaporation of water, which is why we sweat, cools our body surfaces when water pulls heat from the body as hydrogen breaks. So when you sweat, the reason you do that is because you do that, and in order for the water to evaporate, it has to suck up your heat, which means it cools you down. Water molecules in ice are spaced farther apart than the water. So because ice is less dense, it gets to float on the top. That actually, I know it's weird to think of ice keeping everything warm, but the ice can insulate the water below. So even if it's freezing on the top of the ice, maybe under the ice it's not. And water is a polar molecule, which allows it to dissolve other polar molecules. Many kinds of ions and molecules can move freely in and out of cells in a water solution, which means since water is so good at dissolving things, lots of things like salt can be dissolved and move in water without having too much trouble. And our bodies kind of need stuff like sodium and chloride ions in order to survive, the stuff in salt. And go ahead and watch the next video for lesson 2.